Today we're going to begin Unit 2, Topic 2.1, Systems and Center of Mass. So, in the last unit we applied the object model. The size, shape, and configuration of the object are ignored. That's how we analyze all objects in kinematics. What if we had multiple objects? In physics, a system is defined as a collection of objects that can be analyzed. The behavior of the system of objects is dependent on the constituent objects in the system. If the properties or interactions of the objects in a system are not important in modeling the behavior of the system can be treated as a single object. So in other words, let's say we have a plank with two blocks resting on it, sliding across a ramp, the gray ramp depicted in the slide. Since the blocks and the plank are stationary relative to each other, we can treat what we call a two-block plank system as a single object sliding down the ramp. Individual objects within the system may behave differently from each other as well as behave differently from the system as a whole. So let's say we have this system of three objects. We're defining it as a single system. The overall velocity of the system is indicated in the bold arrow, the vector. But notice how the system's overall velocity is different from the individual constituent velocities of each object. And we can label this as the velocity center of mass. And as variables external to a system change, the substructure and behavior of the system may also change. So if we apply an external force to the first ball, we see how the velocity of it changes, but also the center of mass. So when we see a simulation, they do overall change direction. But we also need to determine where that velocity is directed at for the overall system, and where it is directed at is the center of mass. All systems have a center of mass. Each system can be modeled as a singular object that is located at the system's center of mass. And so we have this two-block system here. The center of mass is on a line that connects the two individual objects' centers. And for systems with symmetrical mass distributions, the center of mass is located on a line of symmetry. So the same example before. But what if we set the second block equal to the first block in mass? We can see how the center of mass shifts to be at the exact midway point between the two blocks or ball spheres, whichever you would like to call it. The location of the system center of mass along a linear axis, one dimension, can be calculated by the following relationship. Or at least for this example, it is the x position, center of mass subscript, is equal to the quotient of mass 1 times position 1 plus mass 2 times position 2. And divided by the sum of each mass, the sum of the masses. But that's only for this specific system. That's for the average position of this system. What if we continue it for every additional mass that you add along this one dimension? You get to you can create a formula here, which is called the summation. So this is called a summation symbol, and it basically means the sum of this product over and over and over again. Same with this, the sum of this mass over and over again. So the sum of the whole mass of the system. And that's the equation for the center of mass for I number of objects. We can try doing this as an example. So if we set the origin at mass 1 and set mass 2 L distance away from mass 1, we can continue with the calculation that we had before, the two objects, so mass 1 x1 times plus mass 2 position 2. The first position or the first mass is at 0, so we ignore that. But we still factor it in when we are adding the masses in the denominator. So what we result in is the center of mass being m1 over times L divided by 2 times mass 1. And that leaves us with the center of mass being at 1/2 L. Center mass calculations can also include systems that are in 2 dimensions. So, for example, in this one, we can try finding the center mass along the x-axis and then the y-axis, and then we can determine using those two the actual coordinate of the center of mass, which is at the x and y point of the center of mass. And for in the context of AP Physics 1, they only expect students to calculate the center of mass for systems containing configurations with high symmetry, so on the right image here, and then 2D configurations with 5 or fewer particles. Not bad. Alright, thank you for watching. I'll see you next time.